Hello, everyone. It's our pleasure to have Leo here to share about his recent work on the accuracy versus memory advantage in the quantum simulations of stochastic processes. I think this work should be the first type of like stochastic processes related to quantum machine learning work in our QMS seminar. So it'll be um, interesting to hear Leo to share about. Leo, the floor is yours.
Hi. So hello everyone. So it's a pleasure to speak to you. So I want to thank Bank, Kishore, and Alessandro for the kind invitation. And indeed, today I will speak about this accuracy versus memory advantage in the quantum simulation of stochastic processes. And this is, oops. So this is based on this recent work that has been published a few weeks ago into this IOP machine learning science and technology journal. So all of my talk is based on this paper. So you can find all the details here. So let me introduce what kind of problems I studied in this paper. So the focus was on temporal stochastic processes. And as an example, so here I basically saved the exchange rate between the euro and the Singaporean dollar on last Friday. And so the idea is that you have access to, let's say, the past information. So for instance, the market value at a certain time, and you would like to predict what's going to happen in the near future. For instance, suppose that you're planning a trip to Italy and you want to save a few bucks and optimize, let's say, the time of the year to come here. So that's somehow something where you might want to predict what's going to happen in the future. How can you do that? Now, right now, you might know that there are very popular machine learning techniques based on the transformer architecture that are pretty good at predicting, let's say, at dealing with languages and at predicting, let's say, the next word in a sentence or something like that. And the question is, for instance, can you apply the same technique for predicting like stock markets or stochastic processes like this? It's a legitimate question. I don't have a background in finance, so I asked myself the same question and I Googled it, and Google sent me to this discussion over Reddit. And according to the answers in Reddit, so there were a few answers, but for instance, you might find here a few selected ones. And so if you read, for instance, the second one, they say that the languages have rules based on syntax and attention. And I think the prediction of the stock price use a more traditional machine learning approach with lots of input parameters from the outside world, like news, politics, and so forth. There was also the other thing that basically they say that there are more robust approaches to this, since the uncertainties introduced by any deep learning model can be devastating. Now, this is, of course, just some two random guys over Reddit. They don't even have the real names, so can we trust them? Well, I asked them the same question to the AI itself and said, are transformer-based algorithms the best for predicting the stock market? And the ChatGPT answer was that simpler models or hybrid approaches yield better results due to their robustness and lower risk of overfitting. So if even the AI itself is not super confident about their technology, then I think we are better to use more traditional approaches. So what are these more traditional approaches? Again, I'm a physicist, so I don't have any background in finance, but I have attended a few conferences which were sponsored by the Simons Foundation. And perhaps you know that Simons of the Simons Foundation is the same Simons of the Chern-Simons theory, but it is also the same Simons that established this Renaissance technology firm. And they basically were doing like portfolio optimization and prediction. And they were using an improved and expanded model from Baum's mathematical model. So this is something from Wikipedia. The mathematical model is something clickable, and if you click on it, you are redirected to the Baum-Welch algorithm for hidden Markov models. So it seems that this is the, let's say, well, they managed to make a lot of money using this technique. So it seems that this is one of the traditional machine learning approaches for this kind of temporal problems that are most effective. So let's try to stick to this language. So how can we rephrase the problem in this language? Well, we have something like this. So suppose that today we are here in this white spot. So we have observed the euro versus Singaporean dollar exchange rate, and we would like to predict what's going to happen tomorrow. Now, it's kind of silly to think that one is able to do this by just observing the euro versus dollar, Singaporean dollar value, because this is correlated with many other variables. And so we observe also some part of the market, but we can observe everything. We cannot observe everything. So there will be something that we simply don't have the resources to check. And so that's what we did. We can do today, but we can also read what happened in the past. Again, we can look at the euro versus SGD value. We can also check part of the market. And but then, of course, there is a huge set of unobserved events which are kind of correlated. So this blue spot here means kind of correlation. So the value of today depends on the value of yesterday, but also on the rest of the market that we have observed, but also of the rest of the market that we haven't observed. And so the same is true for tomorrow. So we don't know what's inside this blue spot here, but having known what's here, then we can also predict what we care about. So this euro versus SGD, the rest of the market, although we don't really care about that. And then the unobserved, of course, we cannot make any claim or any observation there. So this whole temporal structure can be written in this language. So let's say we have, so time here goes in this direction. So we have some observed events, and then we have some hidden events. And then let's say in time, so the observed events and the hidden events are correlated. So at certain times we measure and get our observations. And then let's say we repeat this process for many times. And so what we care about depends on all the hidden variables, which in our case were, let's say, all the stock market, but not just that, just politics, I don't know, natural disasters. So everything can influence the market value. And of course, we cannot aim to have access to everything. But the point is that not all of these hidden variables are relevant for predicting the future of observations. So what we can do is that we can replace the hidden variables here with something which is just a memory. And in this memory, we should only put, let's say, what we need to predict the future observations, nothing more. And so the way this model works in hidden Markov models, we have, let's say, a temporal structure which is like this. So every time step is replaced by a single tensor, which is time independent. And so this tensor is a transition matrix. So, so in principle, it could depend also on the past observation, but this dependence is removed. So the transition matrix is an object which is like this. So it's a three-leg tensor, where somehow this beta here is the value of the memory at the previous time. And then it's like a conditional probability of what's the next outcome, which is this x of t plus 1. And what's also the next memory state, which is this mt plus 1. But the whole point is that this is also independent on t. So at all the times you repeat the same matrix. By the way, I didn't say this at the beginning, but if you have any questions, then please do interrupt me at any point. Don't just wait for the end. So if you know the rules, And that's already a big assumption that we might not know what's this T, but suppose you know T. So suppose that you know for this transition matrix because of some models that you already have. Then you can infer future observations via the Bayes rule. So basically, you can use this Bayes rule so that the probability of getting, let's say, some future given the past can be written in terms of a probability of the future and the past together divided by the past. And so all these probabilities can be expressed using this structure here. And from the same rule, basically by keep repeating applying this transition matrix, you can also check what's the probability at a certain, so after some time, to have the memory in a certain state. And this is with, again, using the Bayes rule, you can write this probability in this way as a product of all the transition matrices with the X belonging to the past observation, and then you have some initial probability that's some initial probability about the initial memory state that you normally don't know. So in the most general case where you don't know, on the other hand, the T, so this transition matrix, so this transition matrix can be learned from the data themselves, and let's say the standard approach for doing this is basically maximum likelihood. So you define like a likelihood function of your observations, which is nothing but this product of transition matrices. Remember that for a given X, this transition matrix is just a matrix, it's not a tensor. So this is just a simple matrix vector multiplication. And then at the end, you sum over the memory state because you don't care about the memory at the end. So there are efficient ways of, let's say, getting the T given the past observation. And the Baum-Welch algorithm, which was the one used by Renaissance Technology, is just one example, one efficient example to do this. Okay, so now let me jump to the quantum part. So the point is that you can also use quantum simulators for doing the same thing. So rather than just a completely classical hidden Markov model, you can also use quantum techniques for simulating temporal stochastic processes. And there are many papers doing this. Let's say the ones that I'm more familiar with, there are many papers also by Miele's group in Singapore, Miele and Jane's group in Singapore. And there are also let's say, a related paper by Sirac and Isert's group, which discussed a similar technique. So in quantum simulator, we have a structure like the previous one, but instead of having the transfer matrix here, we replace that with Krauss operators. And so this evolution here, although it's written like in the previous case, so now everything was in the language of probability. Now everything is the language of quantum states. So let's say this now define what is called the matrix product state, where let's say the physical indices are basically the observations, what we care about. And then the hidden variables are the ones that define the bond dimension of the matrix product state. So the biggest difference is that now the probability of getting an outcome is again given by this matrix product structure, but the matrix product structure defines an amplitude, not just a probability. So in order to get the probability, you have to take the amplitude square, well, the absolute value square of the amplitude. And in general, you can ask, let's say, what's possible using these two models. So let's say a completely classical hidden Markov model, or let's say a quantum model where, let's say, you have this amplitudes with Krauss operators. The problem is that in general, these are very different models. So one uses probability, the other one uses amplitudes. And so it's quite difficult to make a fair comparison. But it turns out that people have done that. And so, for instance, these are a few pictures that I took from this Glasser paper. So there are different models. So this matrix product state model, where somehow you model. So this would be the probability of some observation. So X are the observation, and you model this probability in this way, like a direct matrix product structure. So that's the one in this conventional approach. That's to say the tensor form of this expression here. But then you can also use what they call like a Born machine, where this expression here is now a bra and a cat. So the matrix product form is not in the probability, it's in the amplitudes, and then you get the probability by just taking the amplitude square. So this, what they call the Born machine, is, let's say, this part here in this language. And then there is also something which is more general, because you can also use like mixed states. And for mixed states, you can use this trick of locally purified, and let's say the tensor diagram can be written in this way. Okay. And what they discuss in this paper is that they do these comparisons in terms of the expressivity of these models. So, for instance, the standard hidden Markov model is this, let's say, what they call the tensor train. And they use real positive numbers because these are probabilities. While for matrix product states, we use this, let's say, general complex numbers. And they studied the rank. The rank is basically the size of this extra bond in order to make the comparison. And they did show that basically there are some, so for instance, we are interested in the comparison of this and this. And they did show that there are models where somehow one is better than the other and the other way around. But they found that there exists a family of tensors in such that, let's say, the Born rank is 2, while the TT rank is bigger than n. So this means that somehow there are models where, let's say, the quantum simulators use, let's say, a very small bond dimension, while the classical simulator have a dimension that grows with this n, which is the number of binary variables. So these are more like existence theorems. So as far as I know, it was not clear how to efficiently map one problem to the other. So that, let's say, as far as I know, was discussed in this paper by Mila's group. And the idea there is as follows. So suppose now that the transition matrix can be factorized in this way. So remember that the transition matrix, so X is the future observation, beta is the past memory, and alpha is the future memory. So from the past memory, you emit an observation. And then once you know the past memory state and the observation, the transition from the past memory and the observation to the future memory state is deterministic. Okay, so this is an example of model, and they did show that basically when you have a model like this, then you can write the cross operators in terms of this A tensor, and the A tensor is just the square root of the previous tensor of the, let's say, the transfer matrix. And then you have, let's say, these W operators, which are used to normalize the cross operators and make it define like a completely positive trace preserving map. So it turns out that somehow a mathematical structure like this is the one defined by epsilon machines. So what are these epsilon machines? So these epsilon machines are, let's say, they are informationally theoretic optimal models in this sense. And so they have been studied quite a lot in the past 30 years or more by Crutchfield. So the idea, to the best of my understanding, is as follows. So given an observed past, so the memory should only save the information that is relevant for predicting the future and nothing more. So given a past, the memory can be written in this matrix product form. And so if we, let's say, average over the observation, you realize that this asymptotically converges to the steady state pi of the transition matrix, which is the one where somehow you average over the possible observation. And so the information from the past can be quantified by the Shannon information, because now pi is a classical probability distribution, and you can compute the Shannon information from that. So the optimal models in terms of the memory should basically minimize the memory, but in such a way that somehow there is no uncertainty about the future. And this can be written in an information theoretic, let's say, language by asking that the conditional mutual information of the future given the past should be 0. So if you use all these techniques, you realize that somehow everything can be written in the language of an equivalence class, that true past observations are equivalent if basically they give you the same probabilities for the future. And so the central observation is that this equivalence class is the only information that you need to save in the memory. And by thinking about the math on how this, let's say, equivalence class works, then you realize that this results in a deterministic update rule like the one shown before. And then again, what they did show in this paper is that, again, you use this epsilon machine structure. You can also study now the memory, the quantum memory of the quantum simulator. So the quantum memory is now the one can be understood by solving this steady state of the completely positive map defined by the Krauss operators. So previously it was the steady state of this, let's say, transition matrix. Now is the steady state of the quantum map. And let's say the central observation is that the steady state of the quantum map depends on the steady state of the classical map times these W operators, which are the one used to normalize the Krauss operators. But since these W's are not unitaries in general, then I mean there were several follow-up papers by, again, Miller's group that basically show that somehow the entropy of this steady state is always, at least is not bigger than the entropy of the classical simulator. And here they discuss an example where you see a very different dependence on the size of the problem. So the summary here is that somehow there are models that allow you to use, let's say, quantum tricks in order to save memory.
Sorry, I have a question here.
Yeah.
So yeah, just very generic questions, like is the K and the W's easy to find, or like you have to assume special structure in order to get that, right? K and the W's.
So provided that T has this epsilon machine structure, then A is defined by T.
Mm-hmm.
Okay, and then these W are just normalizations. So they are just computed by requiring that this A do not define like a completely positive completely CPT map.
Mm-hmm.
They don't define a CPT map. In order to make them a CPT map, you have to normalize them, and these W's are the ones that do this normalization. So basically, you solve a problem like this, and from like an eigenvalue equation of the map, you can get the W. So it's something which is given the A, but let's say the expression is a bit cumbersome. Well, it's not cumbersome. It's just the solution of an eigenvalue equation.
I see. So the centerpiece over here is the transition matrix T, and then from there you can construct everything accordingly.
Yes, exactly.
Okay, thanks.
Okay, so as a summary, so quantum simulators are more expressive than the classical hidden Markov models, and this, I mean, this claim can be written in terms like there exists some stochastic process such that basically the corresponding memory dimension is smaller. So that's somehow it's more like let's say for some problems, quantum, it's better to go quantum. And then these models that admit an exact epsilon machine structure, for these models, you can show this rigorous advantage using information theoretic techniques. Now, the questions I had were basically two. So first of all, real-world models cannot be exactly expressed as an epsilon machine structure with finite memory. And also, we should expect imperfect simulation. And so my question was to study whether the advantage persists. So that was my main motivation, which was the one actually, let's say, studied in this paper here. So let me tell you also, before going, so the math in that paper is not particularly complicated. So I would like to clarify the idea behind it and the assumptions behind that paper. So the assumption goes like this. So suppose that we start from a real world problem, and we can study this real world problem using classical techniques. So for instance, hidden Markov models. Now, I would like to find the mapping to a quantum problem, which in principle has the same accuracy. And I would like somehow, so you see that this is the memory size. So I would like somehow this to be lower than this. So I would like to have like a quantum simulator of a real world problem to have a smaller memory. And the point is that I don't know any way of doing like a direct mapping between these two. I can do everything numerically and see what happens, but there is, let's say, no theory to drive my numerical simulations. So the assumption behind that work is that there is an epsilon machine, let's say possibly with a bigger memory, because an epsilon machine is uses some restrictions, right? So if you use some restrictions, so perhaps you might need a bigger memory. So the assumption is that somehow you can jump from this to this, let's say, by increasing the memory. And now, once you're here, now you can go to the quantum part in a rigorous way because of this work by Mile's group. And there you have like a direct mapping, you have a rigorous mapping, and you get the same perfect accuracy. And now, once you're here, you want to, let's say, go back to the original problem, so to the original memory. And in principle, you would like to, let's say, get the same accuracy of the original problem, but with a less memory. So is this, let's say, mapping going from here to here possible? Well, maybe. The big problem is that I really don't know how to make this mapping here. So given like a real world problem, so I don't know how to get like an epsilon machine structure. There were some code on GitHub written, I think, by Crutchfield's group, but I didn't manage to, I mean, the code was broken, at least in my computer. So I didn't know how to write that. So, okay, I started basically from another point of view. So I started from a toy problem that can be expressed as an epsilon machine. Then again, we can have like a rigorous mapping between the classical and the quantum world. Now I do the compression in both cases. So I do the compression here in order to get like a real world problem. And I also do a compression here. So in doing this compression, we lose the epsilon machine structure. But that's actually what I wanted, because so the starting point for me is the other case where somehow these real words are not defined with an epsilon machine. So in doing this compression, we lose the epsilon machine structure with the idea of, let's say, going towards the real world applications. So if you have any questions about this, that's maybe the right time to ask, because now, let's say, I will show you also some other examples. But that's somehow the intuition, the main let's say, idea behind this work. And okay, so this is also part of the story. So I told you the story about stock market and whatever, but that's not actually my story. I mean, of course, it would be nice to I don't know, predict market and make money, but that's not the story for me. So the story for me is that let's say I came from this paper here where we were studying generalization in quantum machine learning. And we also did like, let's say, a much more extended paper right now where we also discuss, let's say, the measurement shots, so how the measurement shots affect the generalization. And so in what we discussed in this paper is that, so the generalization error can be defined like this. So normally in a learning problem as a function of the model complexity, you have like the training error decreases. More complex models are always better. But then after a certain point, the testing error starts to increase. And then basically the difference between the testing error and the training error is what is called the generalization error. And what we did show in this series of papers is that this generalization error can be written in terms of information theoretic quantity. And for me, I was interested in understanding whether we can find quantum models that generalize better with less classical data. And in our paper, we did show that the generalization error depends on how much the information is compressed into the quantum state. So the main driving motivation for me was to study whether a quantum advantage in compression, which is kind of what we get from these quantum simulators, result in a quantum advantage for generalization. Okay, so I have to say that this is currently still an open problem for me. And so this paper was more like an initial attempt into that direction. So in what we did study, for instance, in this paper is that exactly, so this generalization error depends on some information theoretic quantities, which is basically, so X is like the classical input data, and Q is the space of, is the quantum state. So this Q now could be like the quantum memory, and X is the classical observations. So you see that somehow in order to make this small, you have to make T, so number of data much larger than this quantity here, which is the Renyi mutual information between X and Q. But if in Q we use pure states, here we can replace this mutual information by just the standard, well, the von Neumann, not the von Neumann, the Renyi entropy of the quantum memory. So the hope was that somehow this advantage in compression could result in better generalization. But as I said, that's still an open problem. So let me say what I did. So again, I started from a toy problem. I constructed like an epsilon machine, and then got to the quantum case. And then consider, let's say, compression techniques in the classical and quantum case. So in the quantum case, I used a very standard compression technique, which was based, it's basically the singular value truncation technique, which is the one used mostly in, let's say, many-body theory with tensor networks. And I couldn't find really something similar for classical hidden Markov models. There were some algorithms, but they didn't work at all when I tried to implement them. So basically what I did is just to define something which might be new, a new compression method for classical models, which are kind of inspired by this SVD spectral truncation method for let's say, for these processes. So, okay, so maybe I'm a bit late, so I will skip this part. But anyway, so the quantum compression part is really standard. So it goes back to this paper by Horus and Vidal. So you basically compute the singular values of the, let's say, of the map, and basically you truncate with some projection. And then you have to normalize, which is given by this. So, so what I did for classical models is something which inspired by that. So because let's say the main intuition of this, let's say, quantum compression is in such a way that somehow so the steady states so what we do is that basically you compute the spectral decomposition of these projectors, so of the steady state. And somehow the memory of the steady state depends on this lambda. So what you do is that you truncate this lambda by getting rid of the singular values, of the smallest singular values. And in this way, you don't change much the memory of the steady state. So I try to do something similar in the quantum case. So I started from the steady state of the original map. Then I kind of got rid of the small values of the steady state, and then you normalize this, and then basically again you used tricks from conditional probability to define, let's say, this reduction map as a kind of conditional probability like this. And so now that we have discussed, let's say, how to compress the quantum and the classical simulators, we have also to define a way of comparing the performance of these two. And so here I defined, let's say, a few figures of merit, but there were also similar figures of merit discussed in this paper here, again by Changran and Miles' group. But so here, suppose that we want to compute the accuracy between two quantum simulators. So one with cross operator A, the other one with cross operator B, and an initial memory, which is this sigma. So I can basically study the fidelity between the two mixed states after tracing out the memory. So I call this rho the state after tracing out the memory, and similar for B. So this is the fidelity between two mixed states which are written in the matrix product state form. And there were, again, let's say, known techniques to do that. So in principle, we can write this as a one norm of a linear map, which is where this linear map is constructed using this A and B. Notice that A and B can have different dimension. So this is not this is like a rectangular map. So this Y is a rectangular matrix. It's not a square matrix. But you can compute the eigenvalues of this map. And basically, so what you realize is that somehow this power here decays. So this fidelity decays exponentially as a function of L, where L here is the number of times. And so you can also study the decay rate and this is what I call here H A given B as the limit for D goes to infinity of let's say this divergence here, which is like a Renyi divergence. And this can be computed explicitly given the largest eigenvalue of this map. Okay. Now, for classical simulators, you can do something like this. You can study the Bhattacharya coefficient or the cosine similarity between the stochastic processes. And the whole point is that anything that depends on the overlap between two distributions can be computed efficiently. While, for instance, the Bhattacharya cannot be computed efficiently, but the overlap, like the cosine similarity, that's efficient. Okay, so then, as I said, I started from a toy problem. So, and I used the same model that was considered in this paper, which is that of a stochastic clock. So imagine that you have a clock. The clock basically starts from 0, and then let's say with some probability you go to the next tick, which is this point here. But then again, with some probability, you reset the clock and it goes to 0. So whenever you increase the clock, you emit an observation, which is 0. Whenever you reset the clock, you emit another observation, which is 1, and you go back to 0. Now, these probabilities, which are these numbers here, are optimized in such a way that somehow the distance between two ticks is uniformly distributed between 0 and n-1, where again here n is the number of ticks in this stochastic clock. And so this is what I did try. So for instance, I did try with let's say with a quantum simulator starting from n equal to 32, And I basically used the 100 million samples. So this is just very efficient to get. I did everything with my laptop, so that's not particularly fancy. So you see that somehow with the exact simulator, you have an almost flat distribution. Now you do the compression part, which basically saves like 50% of the memory. And you see that everything, I mean, it starts oscillating, but it's still pretty good in my opinion. And what I was a bit surprised to see at the beginning is that if you increase the memory, of the problem, so you start from 64 and then again you divide by 2 the memory, then again you get some results which are even better. So perhaps the scaling is favorable for us. And then I also did study, let's say, all this figure of merit. So for instance, I did compute the entropy, which is as a function of how much memory we need to store, and then the accuracy of the simulator, which was again quantified by this divergence between the exact and the compressed simulator. And you see that somehow, of course, whenever you reduce the memory, whenever you reduce the dimension of the tensors, the memory is reduced, but somehow also the accuracy gets bigger. And here also I did compute what happens, let's say, for each n. So for each n, so I studied the compressed simulator by truncating the memory to something which is, I mean, n is the initial memory dimension, and by going to numbers which are as few as n. And you see here that somehow all this decay is pretty close to 0. So that the error that you do with this truncation, as long as you don't truncate too much, is not too high. So as a summary of this numerical observation, I think that this compression algorithm is pretty good, at least in the quantum case. So, and then I think, so that's the most important part. Then I did the same for the classical model and studied the similarity. So now I cannot use this fidelity anymore because there isn't something similar for the classical models. So I focused on the similarity, which is basically a normalized overlap. It's like an inner product distance between these two distributions. And you see that somehow, so everything is done as a function of m. So n is the dimension of the problem. So then I do the truncation, and I truncate to different n. You see that somehow for the quantum model, so the similarity, so the logarithm of the similarity, so it's basically defines how different they are. So it's basically 0. So that means that the similarity was pretty close to 1 for quite a lot of values of m. So truncation didn't affect much the accuracy of the quantum model up to a certain point, and after this point somehow then the accuracy starts to increase. While on the other hand, for the classical models, you observe already, let's say, quite a big change in the prediction, even with a smaller compression, and this then saturates at a certain point. Then I did the same plot. I plotted something slightly different. So just instead of plotting the rank, here I did the same in terms of the memory entropy. And again, you can also see the advantages of these two simulators in terms of accuracy versus memory. Either if you quantify the memory by the dimension of the tensors or by the entropy. And then finally, so these are just the final slides. So this was, let's say, that's not a learning problem because we assume to know the transfer matrix. So let's see what happens if we try to learn the transfer matrix from the data. And so what I did here is just, again, the usual maximum likelihood technique. And so so something that I mean, I found in that paper, I don't know if it was already known in the past, but something that I found quite useful is that the gradient of this of the log likelihood can also be written in terms of normalized quantum states, which are the forward and backward states. And if you do this, somehow you avoid the exponentially small terms, because this term here gets exponentially small as a function of L. And so what I did try, what it happened in my numerical experiments is that when L was pretty big, like 1000 or something, then somehow, this getting this P directly, it was much below the 10 to the minus 16 machine precision of my laptop. And so, well, I got very noisy results. While on the other hand, using this trick here, everything was solved. So we don't have to compute anything which is exponentially small. And so we could do the numerics pretty reliably. So the trick is that somehow, even if this is exponentially small, you can write the gradient of the likelihood in terms of this, let's say, B and F states, where the F states are forward states that you start from, let's say, an initial memory state, and then you keep applying the cross operator with a certain X. So this is not a unitary, because the unitary would be when you sum over the X, it would be like a quantum channel. So that's, you have a properly normalized state. So this is not normalized, so you have to normalize every time. So these are the forward states, and then you get the backward states that you start from the last F, and then you go backwards in time to construct these B operators. And then once you have that, somehow the G is written as a sum of these operators here. So you can get the gradient without exponentially small terms, but you can also get the maximum likelihood using the normalization factors from these forward operators. And again, these are not exponentially small, so you can get everything in a reliable way. Now, so once you have this gradient, you can do like a naive gradient descent, or what I did was just to do like a direct optimization, because these cross operators define mathematically what is called a Stiefel manifold. So one can do Riemann geometry on that, and basically you can find this is like an update rule that maps you directly from the space of normalized cross operators to normalized cross operators. So you don't have to somehow fix the cross operators in order to define like a CP map every gradient step. So, and then again, as I tried applying this, and in the classical case, I did use, let's say, the conventional Baum-Welch algorithm as a reference. And you see, I mean, it's not particularly clear from this expression here, but let's say, for instance, in the classical, so the classical model here, you see that somehow is like a staircase, while the quantum model is slightly better, or at least, I mean, it doesn't have this bump here, and here is much more consistent. Now, when you compress, it is slightly less clear, but you see that the classical model still have this this jump here, while the quantum model is better. And then I also tried, let's say, a real-world example. So I took this lymphography, whatever data point from internet. So these data points are written like this. So in this data set, you have like a bunch of predictions, which are like this. So these are different data points, and you have different rows where you have these lymphatics, then other properties that I didn't study. And the trick here is that you use all of these inputs to train the model, and then I want to check, let's say, how good is the model by, let's say, computing the probability of the final 10 observations. So I did study, let's say, quantum models and classical models, and you see that somehow as a function of the dimension, so the quantum model, so this is a probability, so higher is better. So the quantum models had like a better probability, both overall, because this is just the best value I got, and this is also the median after, I don't remember how many, I think 10 repetitions of the optimization procedure. So we have like a consistent advantage in the prediction using the numerics. Okay, anyway, so this is just a final slide just to show how the optimization look like. So you have like an initial decay, then some, let's say, fluctuations here, and then after a while, somehow the model finds the right path, and then after that time, somehow it goes down pretty quickly. So that's how the numerics look like. Okay, so let me jump to the conclusions. So here we focused on studying the quantum advantage in the simulation of classical stochastic processes, and we found that somehow this advantage persists even when we relax the assumption of exact simulation. So quantum simulators can display a higher accuracy for a given memory, or that alternatively can achieve the same accuracy by retraining less information from the training sequence. So that's what we did show, for instance, in these plots here, where you can see a clear separation between the quantum and the classical models. And then in terms of future prospects, the main question for me is generalization. So is try to see whether, let's say, disadvantage in learning disadvantage in the compression can result in the ability of quantum models to learn with less data because of the better compression. And then another possible future prospect is to use quantum tensor networks, where, let's say, we use both like a quantum simulator to simulate these tensor networks in the regime where the bond dimension is large. And then here the caveat is, of course, is that here, let's say, previously, all the tensor were, let's say, unbounded. Well, not unbounded because they were normalized, but they could take any form. While for quantum tensor networks, the tensor have to be written in a circuit form. And so they had to be constrained to a shallow circuit. And then what happens, so whether the advantage persists is just an open question. And in this quantum tensor networks, then one might also study computational advantage, though I'm not so certain about any possibilities to get a computational advantage in this setting. And then, so as I said, I already started, so my algorithm for optimizing these things was inspired by the classical Van-Welsh algorithm, but it would be nice maybe to make like a full quantum version of the Van-Welsh algorithm. So these are all possible directions, and so I thank you for your attention. Yeah, thank you.
Yeah, thanks, Leo, for the very detailed talk on discussing all the like epsilon machines and stochastic processes. For the audience, if you have any questions, feel free to unmute yourself to ask questions or type the question in chat. We have Felix to have a question.
Hi there, can you hear me?
Yeah, I hope I didn't say anything.
Thanks for the talk, very nice. Huh?
I said, I hope I didn't say anything wrong about your papers.
No, this was very nice. Thanks. I have a question. Actually, I'm very curious about the learning bit, and the gradient way that you're using with these derivatives. This looks almost a little bit like a Fisher information matrix. Not quite, but it looks reminiscent, right? So there's a derivative with respect to the individual parts to get the gradient of the likelihood, right? Can you think of this in these terms? Is this a way to maybe get a bound of how well this can do in either case?
Well, the honest answer is that I don't know. I haven't thought about that in the. Actually, I was also trying to do like the quantum bound Welsh algorithm, and I also had some notes. But I had technical problems because, well, I mean, here the intermediate things are not probabilities. So that's, let's say, my trick, but I don't know if it can be written more into. So why do you say is connected to the Fisher information you said, right?
Yeah, it looks a little bit like this. I'm not sure about the sum, but because you're taking the derivatives with respect to each of these individual k's, of a likelihood function. And it is, I mean, it is what you do in Fisher information. The way to saturate the Kramer-Rao bound is to in the asymptotic limit is maximum likelihood estimation, right?
Yes, yes. I think it's actually, yeah, it's a super nice idea. I didn't think about this, but yeah, I think you're right. It's pretty natural. I'm not sure whether this is like what this algorithm is doing, but yes, I agree that somehow the Fisher information could be another way of optimizing this tensors. Yes.
Cool.
Thank you.
Maybe I could ask some kind of simple questions. So just now you compared about the classical and quantum compression algorithm shows the advantage of quantums over classical, right? Just wondering whether is there anything preventing us for getting a good classical compression algorithm that have comparable performance with the quantum?
Well, as I said, so everything here is dependent on this assumption here. Okay, so so disadvantage is so I don't know what's the best quantum compression, and I don't know what's the best classical compression. So I mean, the most rigorous result would be to put here the best quantum compression that you can have and the best classical compression that you can have. That would be, let's say, the best let's say thing for theoretical comparisons. But I don't know which one is the best, but this one is pretty standard in matrix product states. So that's the one that is used in many let's say simulating many particle systems, and also according to my experiments, this really worked really well. Okay, I don't know if it's optimal, but I would say it's close to optimal. So I did try simply by Googling to look for, let's say, other algorithms for doing like a compression of hidden Markov models. And there were papers with several algorithms also based on spectral compression. I tried to implement them, but I got really poor results. So that's the story, okay? I got really poor results, and so maybe I say, or maybe the quantum models are really so much better, but they were really poor, and so I didn't trust these algorithms too much. So that's why I derived like this new one, which is inspired by this MPS technique. Again, I don't know whether this is optimal, but let's say it has the same intuition behind, because the intuition behind this is that somehow you try to reduce the memory, but in such a way that somehow the steady state is as close as much, or has an entropy which is as close as much to the original one. And this one has the same driving principle. So I don't know again whether this is optimal. There might, well, but I would say it's close enough to the quantum one in order to define like a fair comparison.
I see. Okay. Yeah. Another questions on the same slide actually. So over here you compare the classical epsilon machine with the quantum epsilon machines, right? And then basically from Miller's paper shows that you can achieve same accuracy with the lesser memory with the quantum. Just wondering how will the noise affect this kind of advantage? Like whether it's like if, for example, your quantum epsilon machines will experience some depolarizing noise, and how will that affect the advantage, the performance of quantums over here? Like will the gap become narrower or something like that?
Oh, I see. I don't know. So it might be that Miller's group or maybe even Felix have done something along this direction. Not really sure.
I see.
Yeah, but no, the question is that I haven't studied any form of noise in this simulation, because everything was done on my laptop. So here there was no. So so as I told you, so that's for me was something for the future. So to use this quantum tensor networks, basically where the quantum tensor network is just where you basically this structure here. Yeah, this structure here is simulated not with tensors and a laptop, but with a circuit. So this could be like a parametric quantum circuit, for instance, followed by measurement. So now there are also these quantum computers that allow you to get like this inter-circuit measurements, like this ion trap. So this is now possible using nowadays technology also to put measurements there. And in that language, yes. So then study what happens with noise would be very important, because noise is there in the device. But in my case, so I simulated all these tensors like using this matrix product states. So it's a classical simulation of a quantum process, and so I didn't consider noise because everything was classical.
I see.
Classical simulation. Yes.
Okay. Yeah. Tom mentioned something in the chat. As BD compression is not optimal nor always stable, tangent space compression methods are better. Only shown in there is comparison with lower bounds of classical accuracy at fixed dimension showing probable quantum advantage. Okay, it seems like there are some other like quantum compression algorithm that's better than SVD. So, well, as in like basically just like kind of like enlarging the gap between classical and quantum in your scenario if you use the tangent space compression method, maybe. I suppose.
Okay, so to double check this paper. I mean, first of all, it's after my paper. So, but I know that somehow yes. So, of course I don't know this paper. I have to check. But yes, there are alternative compression techniques, even by using gradient descent, that have been used in the past. The reason why I didn't use them is that, well, I also have like a background in many-body physics, so I used to employ tensor networks for simulating like spin systems or whatever. And normally, from my personal experience, let's say this SVD were kind of, well, they were the ones that I used at that time, because using these gradient descent methods, you never know. You have to define like a stopping criterion where to stop the gradient descent. Maybe adapt the learning rate. So there are different things that you have to really fine tune. So I didn't try that direction, but yeah, I agree that somehow the SVD might not be optimal in all the cases, but for what I tried here, I got, I would say, pretty good results with the SVD method.
Let's see. Yeah, actually we're over time for a bit. Maybe let me ask the one final question. Could you go to your summary slide? Yeah, basically just want to ask some questions about the computational advantage, because like nowadays, like in quantum machine learning, people like to use like the third one, not just memory computational advantage. Yeah, because like nowadays people will use some complexity theory to design some like quantum machine algorithm to show for advantage against the classical one. And one is basically by show algorithms or the discrete log routine by IBMs, right? Where they show that if you construct your feature map using this discrete log kind of subroutine, you can achieve probable quantum advantage. I'm just wondering whether you can design sort of some kind of stochastic processes based on this feature map and then show these computational advantages, like how we kind of design the stochastic clock. I'm not familiar with how to design the stochastic map, so I'm just wondering whether this is possible, just like to design some kind of like discrete log kind of transition so that you can do it on quantum instead of classical.
Yeah, as I said, these are questions for the future. I don't have an answer.
Okay.
So what I can tell you is that, so as you are perhaps very aware, is that so most of the claims of quantum advantage in quantum machine learning with classical data, they have some subtleties. Either they use this RAM so it's quite difficult to get like a quantum advantage for a quantum computational advantage for learning problems for classical data. But there are examples like the ones that you mentioned about this, the problem related to the discrete log. So whether there is something that can be written in this language, I simply don't know.
I see.
So
Okay.
I would say it's an interesting question, but I don't have an answer.
I see. Maybe just like someone will bridge the gap by combining these two, because I think that would be the first attempt to answer your third question. Basically just to combine two existing things in the field and into one. Of course, like that could be hard. I'm not sure. So let's see if someone be able to do it. Okay. I think if there's no further question from the audience, we can just thank the speaker again. Like, thanks Leo for sharing your very interesting talk to us.
Thank you.
To bring us to let us aware about like stochastic processes, and maybe in Singapore, people other than middle school people will start to work on this. Okay. Yeah. Thanks everyone,
Bye.
and see you guys next time.
Thank you.
Yep.
Bye.
Bye.